Hello and welcome to the Chemistry Academy. In this video we're going to go over the section 1 multiple choice in the 2019 SQA National 5 chemistry paper. Sorry again that the green screen is out of action at the moment. I've come into some storage issues on the videos, but I'm hoping it will be fixed soon, but maybe you don't miss seeing my face on these anyway. So we'll kick off with question 1. So the information up here is used for question 1 and 2. So the average rate of reaction, remember the average rate is always the change in quantity over the change in time. I always like to put the time in first because that's the easiest number to spot because it's the units we're most familiar with. So you can see the time is 2 minutes, so that means there's a 2 on the bottom. That means then the other number is the quantity, which is 5. So then we have 5 divided by 2, which is 2.5. So that would be C. In terms of then what the units are, if you're ever unsure of the units, you can actually plug them into the equation as well. So our quantity unit was centimeters cubed, our time unit was minutes. So that's like centimeters cubed per minute, or it can be written as centimeters cubed with the minute to the power of -1. What you can't have is A, which is essentially saying per minute. So we would have to go with option B. This element here, because it's got 7 outer electrons, it means it's most likely going to be in group 7. Remember, elements in the same group have the same number of outer electrons. That's how you can tell what group they are in. And that's why they have similar chemical properties, because everything reacts because of its electron arrangement. So if they've got the same number of outer electrons, they tend to react in a similar way. The ion here that's positively charged, so remember protons are positive, neutrons are neutral, and electrons are negative. So if something's going to be overall positively charged, it needs to have more positives and less negatives. The neutrons aren't going to make a difference here. So if we then look down, the one that has more protons and less electrons is D. If we have a look at the other ones to see what they are, C would actually be neutral. It would be a neutral atom because it is equal numbers of positive protons and negative electrons, so the charges cancel out. B would also be neutral, and A would actually be a negative electron because it's got more negatives than it does positives. Question 5 is one of these ones where you have to just kind of read through the statements to find the one that is correct. So you're basically having to rule them in and out. So if we just go through them, carbon dioxide can be a liquid at 40 degrees. So the critical temperature is where for a gas to turn into liquid, it has to be cooled below its critical temperature. So carbon dioxide would have to be below 31 degrees to be a liquid, so it's not going to be a liquid at 40 degrees. Compounds have higher critical temperatures than elements. So if we have a look at the compounds, so compounds would be substances with more than one type of atom, and the elements only have one type of atom. So if we compare those critical temperatures, wrong colour, sorry. So compounds have higher critical temperatures than elements. The pink ones are higher than the green ones, so that must be our true statement. If we just check the other ones just to see why they're not true. Critical temperature increases as relative formula mass increases. So we can see the relative formula mass is increasing as we go down this column, and we can also see that the critical temperature is also well, it doesn't actually also increase because it does look like it's increasing, but then it takes a big drop again. So that one's not true. And then diatomic elements have lower critical temperatures than noble gases. So here we'd want to compare the diatomics with the noble gases, of which there's just helium shown here. So the diatomic elements actually have higher critical temperatures than the noble gases because these are negative numbers. So this is actually a lower, -268 is actually lower than -240 and -119. So just watch out for the negative numbers trap. The SQ like to set those traps quite a lot. So then the shape of this molecule here, this is the trigonopyramidal, you need to know the shapes of the molecules. Tetrahedral, remember, is where it's got, I like to think of it as a four-headed monster. It's got four heads. That would be tetrahedral. Angular is something like water, where it's kind of got an upside-down V shape. And linear would be things that are just in a straight line, so like carbon dioxide or HCl or something like that. Okay, so that would be tetrahedral. That would be angular, and these ones would be linear. Then question 7, which of the following compounds do the ions have the same electron arrangement? So because these are ionic compounds, these atoms will be ions. We need to check to see what their new electron arrangements would be as ions. I've got a lot of scribbles on here, sorry. So if we go back to here, we've got sodium and oxygen. So sodium, when it becomes an ion, it will lose one electron and become 2,8. Oxygen, it has got the electron arrangement 2,6, but when it becomes an ion, it will gain 2 electrons and also become 2,8. So that's actually our answer, this one, because they both have the electron arrangement 2,8. If we just do the other ones though for completeness, you can see how they're not the case, and also practice the skill of working out the ionic electron arrangements. So lithium would lose 1 electron and become 2. The fluorine would gain 1 electron and become 2,8. So they don't match, because that's 2 and 2,8. Potassium and bromine, so potassium would become 2,8,8. It would become like argon. Bromine would become 2,8,18,8. So again, they don't match. And then magnesium and chlorine. So magnesium ion would become 2,8, and a chloride ion is 2,8,8. So again, they're not the same either. Okay, so that's how you would do those ones. It's useful to write the electron arrangements down as well as you go, just to keep you right. So then the bulb's going to light up when both of these substances can conduct. So if these are liquids, you're either looking for an ionic liquid or solution, or something metallic. Okay, so if we look at A, mercury's a liquid, so that's going to mercury's a metal, so that's going to conduct. But copper sulfate is ionic because that's a mixture of metals and non-metals, but because it's a solid, that's not going to conduct electricity, so the bulb's not going to light up here. Copper chloride, that's also a metal and non-metal, so that is ionic. That's a solution, so that will conduct. Sodium chloride, again, a metal and a non-metal. It is molten, so that's essentially a liquid, so that would conduct. So B should light the bulb up. If we just go through the rest though for completeness, potassium and nitrate, that's metal and non-metal, so that's ionic, but because it's solid, no conductivity. Nickel bromide, again, metal and non-metal, and it is a solution, so it would conduct, but if they both don't conduct, the bulb won't light up. And then D, sodium chloride is ionic because you've got metal and non-metal, and it's a solution, so that would conduct. But hexane is covalent, it's all carbon and hydrogen, so that's not going to conduct at all. The only covalent substance that can conduct electricity is graphite, carbon graphite. Water, technically as well, but water's partially ionic, as you learned in the acids and bases topic, so it's not conducting as a covalent molecule, it's conducting when it splits up into its ions, the hydrogen and hydroxide ions. So then question 9, got a good wrap for this one. The solute is what you put, the solvent is where it went, the solution is what you're producing. The end's not the best, but so the solute is what you put, that's what you've been asked about, the calcium hydroxide, that's the thing you're putting in the water. So the calcium hydroxide is the solute, that's what you're putting. The solvent is where it went, so that's the water, so the solvent's the water, and the solution is what you're producing, so in that case that would be the lime water. There's nothing there that's actually insoluble. Things that are insoluble don't dissolve in water. So then here we've got percent by mass, multiple choice question, how lovely. So remember the percent by mass equation is M over GFM times 100. You do get that at the front of the data booklet. What you need to remember here though is this is the total mass of the element you're interested in. So a lot of people think that it's just the relative atomic mass of the element you're interested in, but it's the total mass of the element in that compound. So because we're looking for the percent by mass of nitrogen, we want the total mass of nitrogen in that compound. There's 2 nitrogens in there, so that would actually be 2 times 14, because the relative atomic mass of nitrogen is 14. So there'd be 14 on the top, and then the GFM of the whole compound goes on the bottom. So we have, for the nitrogens, we've got 2 times, I've run out of room here. That line was far too big. Sorry guys. So 2 times 14 here for the nitrogens, 4 times 1, and then 3 times 16. And if you add that all up, it should give you 80. So you'd get, why have I written 14 there when I was telling you it should be 28? So yeah, 2 times 14 is 28. That's the total mass of nitrogen, divided by 80 times 100. And they've not multiplied this out, so you just check the answers there and it's B. But if you were doing this in a section 2, you would need to multiply it out. They wouldn't give you all the marks. So a bit hypocritical, but never mind. I guess they're only giving you 1 mark here, so it's less work for you. So then if you've got an alkaline solution and you're diluting it, for these questions I always like to draw a wee pH scale, just to kind of keep myself right. And I like to put what the ions are doing on the top, because that's usually the most confusing bit. So if we have an alkaline solution, we're starting up here, and we dilute it, it's going to move towards 7. So our pH number is actually going to go down. As we can see, we're going from 14 towards 7. So the pH is obviously not going to stay the same because we're diluting it. The concentration of hydroxide ions is not going to increase because we're moving away from where there's more hydroxide ions. So then, in fact, the answer is D, where the hydroxide ion concentration will be decreasing as we move to them being more equal. There's also a rhyme for this one here. Bases, they're so great. Oxides, hydroxides, and carbonates. So anything that's a metal oxide, hydroxide, or carbonate is a base. So then that gives you your answer A. All of the other things I should say here are salts. The things that end in like ate or ite or chloride or bromide, any halogenide is a salt if it's got a metal at the front of it. Then the molecule, it doesn't have an isomer. Tip here, the smaller the molecule, the less likely it is to have any isomers. So the smallest molecule here is ethene, which would be your answer. For the systematic name one, it's probably a good idea to draw out fully, because sometimes there's some bits in the structure that can be missed from the shortened structural formula that you've given in the question here. So just expand out all the carbons with what you're told is on them, and hopefully you'll then see that there's a gap here. So these 2 carbons need to make 1 more bond, so there's actually a double bond in there. For naming it then, the longest chain we have is 1, 2, 3, 4, 5 carbons long, so it will be a pentene because it's got a double bond in it. We have to number from the end closest to where the double bond is, so it would actually be pent2ene, and the branch, the methyl branch, is on carbon 3, so it'll be 3-methyl pent2ene. Here, a rule of thumb for these 2 product, 1 product questions and addition reactions is symmetry. So what I would always recommend doing is sketching out just the carbon chain of the alkene. So that's 7, 8, and just drawing the double bond in. So don't put in all the hydrogens, just do the carbon chain. So for hexene, that's 6, double bond at 3. Bute is 4 carbons with a double bond at 2. And then ethene is just the 2 carbons. So when I say look for symmetry, you want to see how many carbons are on each side of the double bond. If it's symmetrical, so there's the same number of carbons on each side of the double bond, you will only ever make 1 product in the addition reaction. If it's not symmetrical, like in octuene, then you can make 2 different things, because depending on where that hydroxyl group goes, you will either end up putting it on carbon 2 or carbon 3. For the symmetrical ones, it doesn't matter which side it goes on for when the double bond breaks, because it's essentially just a mirror image of itself. So if it went here, that would be carbon 2, but over here would also be carbon 2, because that would then become carbon 1 if it's closer to the functional group. So always look for symmetry on these. If it's symmetrical, it'll only produce one product. If it's asymmetrical, you'll get two. Here we've got a wee reaction problem solving question. So they've given you a reaction here, and they've asked you to identify what alkene would be produced if you used this ketone instead of this one. So it's kind of like, again, the game of spot the difference. Imagine you are explaining to your friend that's not that good at chemistry how they would convert this molecule, if they had it on a whiteboard, into this one. So they remove the double bond O and add hydrogens, would be my description to them. So that's exactly what we do here. We remove this double carbon to oxygen bond and put hydrogens instead. So that would give us molecule B. And that is our answer. Which line in the table correctly describes the trends going from hexanoic acid to butanoic acid? So hex is 6 carbons, but is 4 carbons, so that means it's getting smaller. Smaller molecules are obviously going to have lower formula masses, so the formula mass is going to decrease. It's not going to increase because that would happen if it was getting bigger. And smaller molecules are more soluble in water, so the solubility will be increasing, okay, because smaller molecules are more soluble in water. So your solubility is going to go up while your formula mass goes down. So the answer would be B. Then question 18, if you had 4 cells with the different metal pairings, when it comes to voltage, remember, the further apart the metals are in the electrochemical series, the higher the voltage will be. The closer they are, the smaller the voltage. So we're asked to work out which voltage you would get for silver and copper. If we look up the electrochemical series, we can see that silver and copper, always press that timer, sorry, are basically right next to each other. They're very close. So they're going to be the lowest voltage out of all those options, so 0.5. The highest voltage you would get between the copper and the silver and the magnesium, because they are furthest apart. Question 19, placing the metals in order of reactivity. It's quite straightforward, common sensey, this one, because you can see Y doesn't react with anything, so that would be the least reactive. The important bit is you know what order you're doing it in, so sometimes I'll write least to most and then put an arrow so I remember what order I'm actually listing them in. So the least reactive is Y. Then the next most reactive, or least reactive, most reactive in the middle is X, and then the most reactive would be Z because it reacts with both things. So that would give us answer C. Then a copolymer is formed when 2 different monomers polymerize. When you're given a section of polymer, what I would always recommend doing is drawing a squiggly line every 2 carbons, because that's then one monomer. So this wee sections in here, that's a monomer, that's a monomer, that's a monomer. We can see then, if we can draw what the monomers are. So we take those sections out and just draw them as we see them, but we don't put the sticky out arms. Instead, what we do is we fold them back in to make the double bond. So that's this monomer here. The second monomer, if we draw that, it's very similar, but it's not got that CHC in the bottom, and again, you form the double bond. So it's told us one of the monomers is propene. This is propene here, because that's got the 3 carbons in the longest chain, 1, 2, 3. For naming this molecule then, we can see there's a chain of 1, 2, 3, 4, so that makes it a butene. And if we number the chain, it would be but-2-ene, because the carbon to carbon double bond is between carbon 2 and 3. So our answer would be C. If it was pent-2-ene, you would have a chain of 5 carbons with the double bond between 2 and 3. If it was pent-1-ene, you would have a chain of 5 carbons, but the double bond would be between carbon 1 and 2. Okay. Then this one is a bit tricky for the gas collection. What you have to watch out for here is that it tells you the gas is soluble in water. So that means any collections involving water are not suitable, because you're going to lose your gas. It'll dissolve in the water and you'll not actually be able to see it anymore. It's also more dense than air, so that means it would sink. So if you were to use D, it would end up falling out of your measuring cylinder. Whereas C, it will fall, but it will stay down the bottom, and it is actually a brown gas, so you would actually be able to see it. I don't know if this one's brown, I think it might be, or maybe it's black, not sure. Anyway, it would sit in there. But in D, it would end up, if it even made it up the tube, it would end up falling out again. Okay, so the one you have to pick here is C. For collecting gases, a gas cylinder works for all of them. So if you're ever shown a picture with a gas cylinder, that's always the best one to pick. But just remember, if your gas is readily soluble, very soluble in water, then you can't collect it over water, or you will lose it all. Oops, sorry. So then the colour of the flame was green, so then which metal ion would have been in the metal chloride? So we go to the flame colours table, which is here, and we can see that barium gives a green flame, so it must have been barium ions that were in the barium chloride, or the chloride substance. The gas that turns lime water cloudy, this is just something you need to know, that's carbon dioxide. Remember the test for the other one, oxygen relights a glowing splint, hydrogen burns with a pop, and there's not actually a definitive one singular test for nitrogen. Nitrogen will put out a lit flame, however so will carbon dioxide. So you can do that test first, and then to see if it is carbon dioxide or nitrogen, you can use lime water. If the lime water doesn't turn cloudy, you must have had nitrogen. If the lime water does turn cloudy, it must have been the carbon dioxide that you had that put out the flame. Okay, so for nitrogen, you have to do a couple tests. But oxygen relights a glowing splint, hydrogen burns with a pop, carbon dioxide turns lime water cloudy. Then the type of reaction here. So this is the best thing to do when you get a type of reaction question is first of all scan the state symbols. You should then hopefully see that all of these are aqueous except for one product, which is a solid, and that's a sure sign it's a precipitation reaction. If the state symbols didn't show that, so you didn't have all aqueous except for one thing that was a solid, then you would have to go through and look to see what other types of reactions it might be. I do have a tutorial video on types of reactions, so go and check that out. That might help if that's something you struggle with, but most of the time it is a precipitation reaction that they've shown you. And then the last question, the spectator ions. So these are the ones that stay aqueous at the end of the reaction. So the best thing to do is look to see what's aqueous at the end first, and then just double check it was in an aqueous substance at the start. So we've got sodium and the nitrate. The sodium was in an aqueous substance at the start, and so was the nitrate. So the sodium and the nitrate will be your spectator ions. They just watched, they didn't take part. And that's the end of the multiple choice section. If you're looking for help with the section 2 questions, they're in separate videos. There's one for questions 1 to 6, and then also a separate video for questions 7 to 13. I hope you found this helpful. Hope your revision is going well. If you did find this video useful, please give it a like. Don't forget to subscribe, and I will see you again soon.